In this video, we're going to talk more about Chapter 18 on searching and sorting. This time we're going to talk about sorting. So sorting turns out to be a really important issue in that, as we've seen previously, the binary search is much more efficient than the sequential search. So if you can keep things sorted, it makes them much easier to find, okay? So sorting things is a good thing. So it's an important problem, and there are lots of ways to sort that are better or worse. And when you get to algorithms class, you'll certainly talk a lot more about sorting, okay? So we're going to start with a sort that does not get a lot of love in the community. It's not very efficient. It's called the bubble sort. It's called the bubble sort, and I've got the image here from the book, the figure 17.8. With an array-based list, you see that it starts and it compares and swaps the first two items if it needs to, okay? Well, it's going to try to go from smallest to largest. So in this case, the 10 and the 7, the 10 is bigger than the 7, so it swaps, okay? It then looks at the 10 and the 19, they're okay. It looks at the 19 and the 5, swaps those. And finally, it looks at the 19 and the 16 and swaps those, okay? So at the end of one iteration of the bubble sort, you have one item sorted, the 19 sorted. That's where it's in gold, okay? You then go back and do it again, okay, and keep sorting it through until everything gets done, okay? So the first time you'll have to make n comparisons, and then n minus 1, then n minus 2, and so forth. So it turns out to not be the most efficient of things, okay? So in fact, we would call this, again, that sum is a sum that you've probably seen before, n minus 1 plus n minus 2 plus dot 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 plus 2 plus 1. It's there on page 1302. It's the n over n minus 1 over 2, which gives us 1/2 n squared. So this efficiency is about n squared, which means that if you have 10 items to sort, it's going to take you about 100 times to do that, okay? Not very efficient, but it will give us the idea. It's relatively straightforward to implement, okay? So we're going to go ahead and take a look at the code here, okay? So let me go ahead and share over to my terminal. Okay, so I'm calling this bubble sort.h. I'm going to include it in a test file, okay? I probably should call it something more generic, so we can put other ones in there as well, but this will be okay for now. Okay, so again, this one we're assuming it's a templated class, okay? And I'm not going to do the test file here. I'm going to do that separately. Let's do class element type. We have our function void bubble sort element type. It's a list or an array called list of element types, and we're going to send it an int of length, okay? Note that if you're having the user input an array, you're going to have to keep counting up to get that length, okay? So we're going to have a for int, using the variable iteration in the book, equals 1, iteration less than the length, iteration plus plus, then another for loop, okay, for int index, so we don't have the same variable. That's why we're not using I. Int index equals 0. Index is less than the length minus the iteration. Okay, so it's going to be less every time we go through. Okay. And then that's index plus plus. Okay. Then we're going to try, this is a comparison here. We're going to say if list of index, so if list at that position that we're currently at the index is greater than the list at index plus 1. Okay, so if this is the case, then we need to swap. Okay, so we're going to say lm type, we need a temp to do the swap so we don't lose anything, equal to list index. Okay, and then list index is going to be equal to list of index plus 1. Okay, and then list index plus 1 is going to be equal to the temp that we saved. Okay. That. So bubble sort. Okay. So that's all there is to it. Pretty straightforward, but it's gonna, you see where the n squared comes from. That for loop's gonna go through n times and then n times again, more or less. Okay. So not very efficient, but should get the job done. Okay. I'm gonna go ahead and change this. Okay, to, let's do this, sort algorithms. .h. So I'm going to move bubble sort .h to sort algorithms.h. Okay, straightforward enough. Okay, let me go ahead and take a look at that, make sure that doesn't have any errors. Seems okay. Okay, so I've already created a bubble sort test. It's also from the book. Bubble sort test. Okay. So I've now, instead of this, I'm doing the sort algorithms. Okay, this one's just going to go through. It's going to create this list, 10 elements. It's going to, it puts a little print function. And we haven't been doing it this way, but I figured I'd go ahead and show this kind. So this is the template up here. Okay, the reason we do this, and we haven't been for simplicity, but the reason to do this is that you can see all your functions at once and get to those quicker. Okay, so then we're just going to print it out. We're going to sort it. We're setting it to the bubble sort, and then we're done. Okay, and then down here is the print function. We're just going through and print stuff out. Okay, pretty straightforward. So if I haven't created a typo, which who knows if I have, nope, looks okay. And I'm just doing the cheap way, the a.out. And looks like it works. Okay, so this again is not a very efficient algorithm, but at least it's fairly straightforward. I wouldn't do this on the job. Not only is it at an n squared, but it also takes a lot of memory to do all the switches and the swaps and all the temps and all that. So it's just not a good thing. Okay. The book then goes on to talk about using bubble sort with the unordered array list. Okay. And it has another function that you can put there. Okay. So it's certainly, that's something to play with. Okay. We may do that in class. We're not. We'll see where we get. Okay. So that's a bubble sort, pretty straightforward. The next kind of sort here is going to be called the selection sort. Okay. So the selection sort has it's a little more efficient. It's at the same efficiency class, but it's doing less swapping. Okay. So the basic idea behind the selection sort is that you're going to go through and test and do what I call the king of the hill algorithm to find the smallest element of the set. You're then going to swap that or move that to the beginning. Okay. So that's basically how that's going to work. Okay. So by doing that, so by finding the smallest element and moving it, we're only moving things one time per iteration. With the bubble, you can move it every time. If you have an inversely sorted list to sort, it's going to move everything every time. Okay, so and that could be a problem. Okay, so let's take a look at this one here. We're going to go ahead and create it again. This is from the book. Okay, so let's see what we're going to call this. We're going to start with how to get that min location. And why am I not? There we go. I'm going to go back to this sort algorithms and put all of this there, I think, just so we can keep them together. Okay, so we have this function here. We're going to create some other functions in this little file that's going to have just some algorithms in it. And we have to start with, we're going to get a function to create or to find that minimum element of a class, so the minimum location. Okay. So again, we're using our class element type. Okay, and I think there was some confusion before about when you need to add that. And this is twice in the same file, but each function needs it as well. I think that's what the answer is. We'll see if it gives us an error. Okay, so for this one, I'm going to create this function called min location. Min location. Okay, which again is going to take the element type list. So it's a an array of the element type, but this time we're going to take a first and a last, since we're dealing with a diminishing set every time. Okay. So we're going to set this int min index variable. Need to have some brackets there. Okay. We're setting up this variable, okay, or initializing the variable, and we're going to set it initially, this min index. We're going to set it equal to whatever that first position we're sending in. Okay. We're then going to do a for int location is equal to the first plus 1. Okay. So again, we're starting the one next to the first, as long as the location is less than or equal to the last, location plus plus. Okay. And now inside of that for loop there, okay, we're going to check to see. We're going to say if the list location is less than the list at that min index. Okay, so the first time through, we're assuming that the first element's the smallest, and we're now checking that. Okay, so if it's true that our new location is smaller than the smallest one, okay, then we're going to let the min index be equal to that current location. Okay, so notice this isn't doing any changes at all. All it's going to do for us is help us to figure out where the smallest one is located at. Okay, if whether it's the first one or whichever one it is. Okay, so that's doing part of the work here. And you could all do this in one function if you wanted, but I think it makes sense to go ahead and break it up here. So we've got a template class element type. Again, this is for swap function, which also takes an array of element types. Okay. And it's just going to take, oh, it has first and last as well. Got lost in my place here. It's got int first and last. Okay. Same idea. Okay. So as with the bubble sort, we have to create a temp. But again, note that we're only doing this one time per whole round rather than bunches of times per round. Okay. So once we've got our element type temp, we're going to let temp being equal to the first. Okay. We're then letting list first be equal, not first last, it's first and second. I knew there was something weird with this one. So list first is equal to list second. And now we want list second to be list first, but we had to save list first as temp. So list second is equal to temp. Okay. That's going to end our swap. Okay. We can now go ahead and create the sort itself. Okay. So again, I'm going to copy this, Control K, Control Y. Here again for another Control Y. Okay. So we can finally get to our void function selection sort, which takes an element type list. So again, array of element types, okay, and a length. Okay. So this, we're again going to set a min index integer. Okay. Then we're going to have for int location equals 0, as long as the location is less than length. We'll let location plus plus. Okay. Then we're going to set the min index to be equal to the result of that min location that we have. Okay. Which is list location length minus 1. Okay, so this location is what's going up. So at the first time, we're starting at the very first element. The second time through this loop, we go to the second element and so forth. That's how we progress through, okay, this, okay? And then once we've determined where that minimum index is, we're going to swap the list. We're going to swap location with the min index, and that will make that swap. And it doesn't like something that I've done. Oh, missing that. Yeah, if you hit return an Emacs and it doesn't go where you think it's going to go, like it should go there, then you know something's unhappy. Okay, so this is going to do the search, right, or the sort, and it's going to be more efficient than the bubble sort. It's still at the same efficiency class of n squared. It's still going to take n squared number of times, but it's more efficient in that there's a whole lot less swapping and a whole lot less of memory agitation. Okay, so that's our second kind of sort. Okay, and we're going to probably the exercise in class is going to be testing all these, but we'll have to stay tuned to make sure of that. So the next sort we're going to cover is called the insertion sort. Okay, and the insertion sort is going to be different in that it's going to have like we've seen before, it's going to have a sorted portion of the list and an unsorted list. And then what it's going to do, it's going to grab the next element that's unsorted and put it in the proper place. Okay, so you can look for examples in your book, but basically it assumes the first time that the first element of the array is sorted, because a one element array is always sorted. You can't be unsorted. Okay, it's then going to grab the second element and see where it needs to put it in that list. Okay, either it leaves it where it's at, or it swaps it. Okay, in either case, now those two elements are sorted. And then as we grab the third element, we put it in the proper place, either the first, second, or third element. We keep doing that as we go through. Okay, so that becomes the basic idea of how this code works. Okay, so let's take a look at how we're going to do this. Okay, so this is in the book also. This is on page 1308, and this is the insertion sort. Okay, so again, we have our, they have the yank still, I do. Okay, so now we can do a temp, no, that's what we just did. We're going to do a void insertion sort element type list int length. Okay, for int first out of order. Okay, so the first time it finds something there, so the first out of order is going from 1, the first out of order, it's hard to type, it's less than length. And then first out of order plus plus. Spelled all out the same, it will be a miracle. Okay, so then we have our if list first out of order is less than list first out of order minus 1. Okay. Nope. I'm missing a parentheses. Come back to me, cursor. Okay, there we go. So then we're going to have our element type temp is equal to the list of first out of order. Okay, int location is equal to first out of order. Okay. Then we're going to do, I don't like it, but we're going to do it, a do while. Okay, so we're going to set that the list location. So we're moving because we're not yet in the right position. Okay, the list of location is equal to the list of location minus 1. Okay, and then location minus decrements that. Okay, I'm going to do this while the location remains greater than 0 and the list at position location minus 1 is greater than temp. Okay, so this loop is going to start, okay, at the first one, that it starts at the first positions out of order. So that's how we're keeping our unsorted and sorted. It's then going to go to the next one. It's going to take the one that's first out of order. It's going to move it from right to left until it finds the right spot for it. Then it's going to swap it. Okay, so that's what this is doing. Parentheses there. Okay, and then finally the list location, which is where we started, is going to equal to temp. Okay. That gets us all the way over there. Okay. So this, I mean, this should work, right? This should be the idea. Okay. This one, when we're looking at the efficiency class here, okay, is also going to be the n squared. Okay, so they're all at the n squared. But there's a little table on page 1309 that shows while the number of comparisons is going to be n squared for all of these, the number of swaps is going to be less for the selection sort, basically. Okay, the insertion sort and the bubble sort both have the same amount. Okay, so these are all considered, not great algorithms. Okay, so where we're headed now, which will be the thing we'll talk about on Friday, is going to be the most efficient comparison-based algorithms we can get. And the book talks about that upper limit on that, the theoretical limit of the performance, but that's more of an algorithms thing, so we won't talk about it. But just know that the algorithms we talk about, quick sort and merge sort, are at n log n, and n log n is as fast as a comparison-based sort can be. Okay, they're a little more complicated to produce, okay, to code and to figure out, but they will certainly be as efficient as you can be. If you don't need to be that efficient, then of the three, the selection sort has the fewest number of swaps. Okay, the insertion sort's not awful. The insertion sort has short code and it's not as bad as a bubble sort. Okay, so those are basically the options we have. Okay, so it's, as the book says, left to an exercise. So we'll do it in class at some point to test these and kind of see their performance in real life. Okay. So that's all I've got for this video. If you have questions, as always, let me know.